So I'll share with you how I did my workings. Hope you can see what is on the screen.
Yeah.
I'm hoping that I've not blocked anybody. I've admitted those who are on the waiting. Good. So our problem now begins. And as we said, there are the following steps which will be required to first of all address before we can do anything else. Number one, do we have the objective for our problem so that we're able to come up with the objective function? Number two, what are our decision variables? Number three, what are our constraints? And then from there, we'll be able to come up with the LP problem. So I'll start by assuming or rating something to be what I want to, for example, come up with. So my problem is how many units of model C1 chairs and how many units of model C2 chairs should we have so that we're able to have maximized our contribution? Because the problem now coming in form of selling price and the variable cost there, then definitely the objective would be on maximization. So we say there are some keywords which will be mentioned in the problem. And even if you are not told what we are doing, you're not given that objective, you should be able to pick it from the keywords which will be guiding you in the problem. So here we are looking at the number of chairs for each of the models, and I won't change the way our models have been defined. I'll still let them to be C1 and C2, and I'll also use those two to define my decision variables. So don't get confused. I've said let C1 denote the number of chairs for model C1. And then let C2 to denote the number of chairs for model C2. I've not changed the name of the model. It's only that I've borrowed the two to still denote my numbers. That is for the two models to be produced. So C1 and the C2 becomes my decision variables. Then what are my constraints? The constraints are the amount of time, the hours for machine X and the Y. And we are also told in the production we require a material called the plastic waste. So it's also limiting us in our production. So those three are the ones which are going to give us the major constraints to be written alongside our decision variables as we form our objective function. And finally, remember, we have to consider that when we are producing, then we cannot have a negative amount of chairs produced. They have to be positive variables. So at the end of the day, the non-negativity condition must also be written down. But now, before we come up with all these, do we have the guiding figures so that we can now formulate our LP problem? I take you back to what we did in our first topic, which we were looking at the functions, and basically from the linear functions, we talked about the CVP analysis. And if you remember, we said a contribution is actually the difference between what? The price per unit of a product and its variable cost. I repeat, a contribution is a difference between the price per unit and the variable cost per that particular unit. So when we are evaluating the contribution per a chair, say by each of our two models, then we'll be using the formula price per unit minus the corresponding variable cost. But now, variable costs were coming in 3 ways. One, the cost as per the use of plastic waste, and also the use of the machine hours, which is by X, and then finally by Y. So those three are going to give us what we can now call the total variable cost. So what I've done in my calculations class, I've picked the selling price. Let's start with the C1 model. A unit of C1 is going to be sold at an amount of shillings 1,000. And we have the amount of hours required to make a unit of C1 from machine X equivalent to 0.5 hours. But a machine hour would cost us how much? Shillings 250. That is for X, and also 300 shillings that is out of the machine Y. So my workings are done as follows. I've constituted what would be the total amount if I were to involve 0.5 hours from the machine X, and again 0.4 hours, let's say by the use of machine Y. But we were also told a unit to be made for each of the chairs then will require 4 kgs of the plastic waste. But plastic waste is also costing us how much? Shillings 50 per kg. So if C1 requires 4 kgs per a kg equivalent to shillings 50, that is where my workings are actually coming from. And in total now, the cost to be the variable cost, remember, shillings 555. You can see what I've done here as my workings. And then finally, the contribution will be given by the difference between this particular unit price, shillings 1,000, then minus 445. The whole of this is coming to shillings 445, sorry, the whole of this. The difference will give us a contribution of shillings 555. That is per a unit of C1 model. Then we also do the same to C2, where again we take into consideration from the first table given how much of the time is required by a unit of C2, 0.3 from machine X and 0.45 from machine Y. So in total, plus remember the plastic waste is also going to cost us. So in total, we end up having an amount equivalent to shillings 410. The whole of this calculation here, let me show you. The whole of that, I've computed it. The whole of this is coming to shillings 410, a difference of 490 as our contribution, say, from the selling price per unit of 900 shilling. So in the end, we can now formulate our LP objective function. Say we said our units will be C1 and C2. So a unit of C1 will give us shillings 555. That of C2 will give us 490. Remember, we are maximizing, so we can call it maximum contribution. My contribution is denoted by Z here, and that would be our objective what? Function. But subject to what? The constraints are now denoted by the following. Let's go back to the data given. We have the C1 using 0.5 hours, that is from machine X, 0.4 hours from machine Y, and we are now going across. Previously, I was using the figures column-wise. Now I'll be using them horizontally, that is from each law. And I'll start with the machine X hours, which will be used by both a model C1 and C2. A unit of C1 would require 0.5 from machine X, and a unit of C2 would require 0.3 hours from machine X. So in total, we constitute an equation, but we cannot exceed the available amount of hours equivalent to 3,400 hours. So that is how I formed my first equation, my first inequality here as a constraint posed by the availability of machine X hours. The same going to machine Y availability. Again, we go back to the data. For us to produce a unit of C1 will require 0.4 hours of machine Y, and the same C2 would require 0.45 hours, that is from machine Y. But again, we cannot exhaust or we cannot go beyond the 3840 hours available. And finally, for the plastic waste, we were told each of the two models would require a unit of each, would require 4 kgs to be made. But again, the only available amount which you cannot go beyond is 34,000 kgs. And as we said, the units of the chairs for both of the two models, C1 and C2, cannot go to be negative. They have to be positive values at the end of the day. So that is our LP problem. And we'd want now to begin by standardizing this particular model. And we set our first table to be able now to solve the problem using the simplex method. Because the problem is on maximization. Remember how we go by standardizing is we introduce what we were calling the slack variables, with the assumption that if there'll be any balance, then I would want to say how much is that balance. That is what we were calling the slack. And we are going to introduce 3 slacks. Remember, we had 3 constraints, and each of the slack will be corresponding to a particular constraint. So S1 is a slack for constraint number 1, S2 for constraint number 2, and S3 referring to the slack responding to the constraint number 3. And when I introduce those slack variables on my objective function, as I take the variables which were on to the right to the left, then it would mean the first solution of our Z, which is our objective actually, will be equivalent to 0. And if you remember, we said the moment you introduce the slack variables, all your inequality changes to equations. So this helps you now to come up with a figure that you can say is equals to what, and this is what we normally put on the right-hand side. Now, after we have standardized the problem, remember the first thing we did is to formulate the LP problem. We have introduced the slack so that we're able to standardize it. Step number 3 now, we are setting our first table. And the first table will be given by, or we do it in form of a matrix, where I'll just get the coefficients of my variables. And this time I have got quite a number of variables because I've introduced 3 more in relation to my slack variables. So before maybe we continue, I would want you to make a small correction here on your objective function. Here we ought to have indicated C1, and again here we indicate C2. I must have missed that, sorry for that. So our coefficients for these particular variables will be used to come up with our first table. Our first table will be given by the coefficients of the C1, C2, S1, S2, as well as the S3. So we set our table, and our interest is on this particular law that we call the Z. After we have set our table, we go straight into our Z law. We ask ourselves, do we have any negative element in law Z? If yes, then the solution is not optimal. If all these were positive, I repeat, if all these were positive, then would have said the solution of 0 is equivalent to the highest value possible, and would have said it's actually our optimal value. But now we still have some negativities on our Z law, and so we cannot call the value 0 here as to our Z optimal. Now, because of these negatives, Z is not yet optimal. So what do? We come up with the highest negative element on law Z, and as we look through, we see minus 555 is actually the highest negative element in law Z, which help us to come up with identification. The whole of this column, we now call it what we are calling the pivot column. I repeat, the highest negative element in law Z is negative 555 or 555, and that guides us into the understanding of what we can now call the pivot column. What is the importance of this pivot column? The pivot column helps us to come up with the elements which will divide the variables which are on the right-hand side, so that we are now able to come up with the ratios. I repeat, we pick our right-hand side variables or elements, and we divide by the corresponding elements in the pivot column to be able to define the ratios. So after we have come up with the pivot column, we are going to pick each of the right-hand side elements or variables, and we divide each by the corresponding pivot element. So we'll start 34,000 divided by the corresponding element here is 5 on our pivot column. We go 384,000. We divide this one by 40, and we finally divide 34,000 by 4. Maybe somebody would wonder, how comes my figures are now larger than what was given previously? I've converted my values to whole numbers. Here we had a 0 point. So I've made my figures to be whole numbers for simplicity of my workings. I don't want to be confused when I'm subtracting and adding, especially where decimal numbers would be involved. So like here we had an inequality of the kind 0.5 plus 0.3. So I've multiplied everything, these two, by the corresponding decimal number being 1. I've made them to be whole numbers by multiplying by 10. And whatever I do to the right, remember, we have, or rather whatever we do to the left, we also do it to the right. So to balance the equation and to retain the same meaning, that is what we have actually considered to do. So our ratio here, after we have divided the right-hand side elements by the corresponding elements in the pivot column, we have the smallest being 6,800. So what is the meaning of that? The smallest ratio, or what we call a ration, help us to come up with what we call the pivot law. Pivot law is the law that corresponds with the smallest ration in our table. And the point of intersection between now the pivot column and the pivot law gives us the pivot element. So our pivot element here is actually 5. Now, I've identified my pivot column. I've defined my pivot law. Pivot column, we have said, is a column corresponding with the highest negative element in law Z. The pivot law is a law that corresponds with the smallest ratio, and the ratio is given by the right-hand side variable divided by the corresponding element in the pivot column. My variable corresponding with the pivot column becomes the entering variable, and it will enter where? It will enter into the space that was occupied by the pivot law. So pivot law must pave way to the element corresponding with the pivot column. And so my S1 law becomes the leaving variable. It will leave so that it can pave way to the entering variable being a C1. So in my next table, would want to come up with the elements which will now give us that entering a variable law, which we are calling the C1. How do we do this? After we have identified class, the point of intersection between the pivot column and the pivot law, which is 5, we'll come and divide all elements in the pivot law by that 5. I repeat, all elements in the pivot law will be divided by the pivot element. And the elements we now get will give us the new law we are calling the C1. So we start, I had the odd values of the C1, or rather the S1, which were 5, 3, all the way to the last one here. And we come and divide by 5 all through to be able now to come up with the new elements, which will give us law C1 as our entering variable. So when we evaluate, I would wish that we stop annotation kindly so that we don't confuse the others. Whoever is annotating on my document, kindly stop it so that we are together. We might confuse others thinking that I'm explaining on that point when I'm on another point. Yeah, let's not do that kindly. So at the end of the day, we would want to know which are these new elements which will give us the new law we are calling the C1. And we have said C1 will be given by the odd elements which were constituting the S1. And we are dividing all through by this particular element, which we are calling the pivot element. So this becomes our new C1 law. What's the importance of this C1 law now? It will help us, class, to come back to this particular table and we convert. You can see the pivot column. There are some elements which are not zeros. And these are alongside law S2, S3, and even Z. They must be converted to zeros. And we'll use the law that we have called the C1 law. So how do we do this? I'll start with the S2 law. S2 law had an element of 40 on the pivot column, and I would want to convert that 40 to a 0. So what do? My new C1 law, here I already have a 1. How can I make this one to help me convert this 40 to a 0? I just multiply by 40, so that I have 40 minus 40 giving me a 0 element at the end of the day. So my elements in C1 are multiplying all through by 40, and then we end up figures having, let's start, 40 by 1, 40 by 3 all over 5, 40 by a fifth, 0, 0, and then 6,800 by 40. Because I wanted to come up with a 0 here, I'll choose the operation of a subtraction, and this becomes my new S2 law, which I'll use now into creating my second table. Again, we go back to the table. We had a positive 4 here on the S3 law. How do we convert this 4 to be a 0 using our C1 law? What I've done, I've picked my old S3 law, whose elements were as follows. Then I've just said, because I had a 1 alongside the C1 here, I've multiplied it by 4, so that I end up having 4 minus 4 to be equivalent to 0 at the end of the day. Don't worry what will happen to all these other elements. Your concern is just to make that particular element to be equivalent to 0 at the end of the day. The same I've done to the law Z, where I had a minus 555, and here I had a 1 according to the C1 law. To make it 0 at the end of the day, I've just multiplied my C1 by 555. But because this operation was a minus, this was a positive, I've combined the two by adding the two laws. And finally, I'll have converted all the elements in the pivot column, apart from the one corresponding with my entering variable. All the others are now converted to 0. So what do? We set our next table. And when we set our next table, remember, we are bringing in the C1 where we had the S1 law, because this was our entering variable and the other one was actually to be our leaving variable. After we set up our table, the question, we said LP involve iteration. We keep on repeating previous stages, yeah? The question is a solution of 3,774,000 optimal? No. Why? Because we still have negative elements alongside low Z. As long as there is any negative, then the solution is not optimal. But if they turn out to be positive, then we say the solution is optimal. Now, because of this minus 157 on our law Z, then the solution of 3,774,000 here, it is not yet the optimal value. So what do? That highest negative element on low Z, the negative 157, help us to identify what we call the pivot column. And the pivot column in this case will be used to divide all the elements in the right-hand side, yeah, the right-hand side variables, to be divided by the elements corresponding in the pivot column to come up with what we are calling the ratios. So we repeat the stage we had earlier on. I'll start 6,800 divided by an element of 3 all over 5. That becomes, in my workings, 11,333 with the 3 recurring there. Then 112,000 divided by 21. In my case, it was coming to 5,333, again with the 3 recurring. Finally, we have 6,800 divided by 1.6, which was coming to 4,250 in my case. And you can see again, it becomes the smallest, yeah, this is the smallest ratio. So what does that one mean? We are able to identify what we call the pivot law. The smallest ratio, we come up with the pivot law. And the pivot law here will give us the leaving variable. The pivot column identifies the entering variable. So the C2, which is the entering variable, will replace the S3, which is the leaving variable. And the element at the point of intersection between the pivot column and the pivot law, this point of intersection class becomes our pivot element, which will be used to divide all the elements in the pivot law. All this will be divided by that corresponding element we are calling the pivot element, so that we can come up with the new elements which will give us low C2. I repeat, the point of intersection between the pivot column and the pivot law is 1.6. That 1.6 will be used to do what? To divide all the elements in law S3 as our pivot law, and the new values that we'll come up with will constitute the new law we call the C2 as our entering variable. So we now divide our S3 law by that corresponding pivot element all through, and we have got the new variables that we can say they are giving us elements to constitute the low C2, where the C2 now will be sitting lawwise as our entering variable. The question is, if we were to go back to our second table, are the elements in the other laws alongside the pivot column zeros? No. So what do? We convert these 3 all over 5, the 21 here, and the minus 157 all to be zeros. So class, I have only 1 minute left. And let me do one law, and then when we come back, we can finish up with the other 2 laws. So I'll start with the law C2. In law C2, what do we have? Law C2, let's start with the law C2. Law C2 is our new entering law, which has these elements here. And they are the ones which are going to use to convert anything else to be equivalent to 0 alongside the pivot column. Okay, so let's start by converting these 3 all over 5, which was alongside law C1 to 0. Because this is